let's begin. Almost every planet in the solar system rotates in the same general direction. This is not something that announces itself loudly. There is no cosmic arrow painted across the sky, no obvious sign that worlds are quietly agreeing on how to turn. The pattern only reveals itself when motion is watched patiently, over long stretches of time with careful attention to detail. From Earth, planets appear calm and distant. They drift slowly against the fixed background of stars, changing position night after night, year after year. Early astronomers focused on these wandering paths, trying to understand why planets looped, slowed, or even appeared to move backward for a time. Rotation was far more subtle. A planet's spin is inward, quiet, revealed only through shadows, surface markings, and the faint clues left by changing light. But once those clues were gathered, something remarkable became clear. Mercury rotates slowly, taking many weeks to complete a single turn. Jupiter spins so quickly that its day lasts less than half an Earth day. Saturn flattens at its middle because of its speed. Mars turns at a familiar pace, giving it days not so different from those on Earth. The speeds vary widely. The sizes could not be more different. The compositions range from rocky worlds to vast spheres of gas. And yet, almost all of them turn the same way. Viewed from above the north side of the solar system, the planets rotate in an anti-clockwise direction. This is true for Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Even Mercury, slow and strange in many ways, follows the same basic sense of spin. The differences lie in how fast they turn, not in the direction they choose. That shared motion is the first quiet clue that these planets did not form independently. Astronomers determine a planet's rotation in several gentle, indirect ways. For worlds with visible surfaces, rotation can be tracked by watching surface features drift across the planet's face. Dark regions, bright patches, storms, and ice caps all move predictably as the planet turns. Mars reveals its spin through changing polar caps. Jupiter's rotation is traced by its cloud bands and its famous long-lived storm. Saturn's subtle stripes and shadows offer similar hints. For planets wrapped in thick clouds, the task becomes more delicate. Venus hides its surface completely beneath a dense atmosphere, but radar observations allow astronomers to bounce signals off the ground below, revealing how the planet slowly turns beneath its cloud cover. In that case, the measurements revealed a surprise. Venus rotates in the opposite direction and very slowly, taking longer to turn once than it does to orbit the Sun. It is an exception that stands out clearly precisely because the rest of the system is so consistent. For the outer planets, rotation can also be inferred through magnetic fields. As a planet spins, its magnetic field rotates with it, sweeping past spacecraft and detectors. These repeating signals act like a steady heartbeat, marking each rotation with quiet regularity. Even when clouds shift or storms evolve, the magnetic rhythm remains. When all of these measurements are placed side by side, the pattern becomes impossible to ignore. The solar system does not behave like a collection of unrelated objects. It behaves like a family. The planets orbit the Sun in nearly the same plane, moving in the same orbital direction. Their moons often orbit in that same sense as well, and almost all of the planets rotate in agreement with that larger motion. This alignment is not perfect, but it is far too consistent to be random. If planets formed independently, scattered through space and later captured by the Sun, their spins would be expected to point in all directions. Some would rotate clockwise, others anti-clockwise, many tilted at extreme angles. There would be no clear preference, no dominant pattern. Chaos would rule. That is not what is observed. Instead, the solar system shows a strong memory of its earliest moments. Rotation appears not as an afterthought, but as something inherited, passed down quietly from one stage of formation to the next. The shared spin is not imposed. It is carried forward. Even the variations tell part of the same story. Uranus, famously tilted on its side, still rotates in the same directional sense when viewed from its own north. Its orientation is unusual, but its underlying spin still fits within the broader pattern. Neptune, distant and cold, follows along as well. Jupiter's immense mass does not break the rule. Saturn's rings, spread wide and thin, orbit in harmony with the planet's spin. The exceptions, like Venus, stand out precisely because they are rare. When astronomers map rotation across the solar system, they do not see disorder. They see a system that began with a shared motion and never fully let go of it. Differences accumulate, impacts happen, axes tilt, speeds change, but the overall direction remains stubbornly consistent. This consistency tells a deeper story than speed ever could. Speed can be altered easily. A collision can slow a planet down or speed it up. A moon can tug on its parent world, gradually reshaping its rotation over immense spans of time. Atmospheres can apply subtle braking forces. All of these processes can change how fast a planet turns. Changing direction is much harder. To reverse a planet's spin entirely requires extraordinary circumstances. It demands either a massive, precisely angled collision or a long history of powerful tidal interactions. These events are possible, but they are not common. The fact that most planets avoided such reversals suggests that their original motion was strong, coherent, and deeply rooted in the system's earlier structure. There is something quietly comforting about this. In a universe that often feels violent and unpredictable, the solar system reveals a surprising calm, not because nothing dramatic happened, but because even drama unfolded within boundaries set early on. Planets may wander slightly, they may wobble, they may wear scars from ancient impacts, but beneath all of that they continue to turn together, keeping time with a motion older than the planets themselves. This shared spin is not a rule written into space by necessity. Other solar systems may spin the opposite way entirely. If viewed from their own north, their planets might turn clockwise instead. Direction itself is not special. What matters is agreement. The solar system chose a direction long ago, and nearly every planet has followed it ever since. That agreement is the starting point for understanding how planets form, how disks of gas behave, and how order can quietly emerge from vast, drifting clouds of matter. It is not a loud clue. It does not sparkle or explode. It simply turns steadily and reliably together. The phrase anti-clockwise sounds precise, almost absolute, but in space it is anything but. Direction depends entirely on where the observer is standing, or in this case, floating. There is no universal up or down written into the universe, no built-in left or right. Space does not come with arrows or labels, it simply exists, and direction is something added by perspective. When astronomers say that planets rotate anti-clockwise, they are quietly making an agreement about viewpoint. They are choosing to look at the solar system from a particular angle and describing motion from there. Without that shared reference, the description would lose its meaning. To understand this, it helps to imagine the solar system not from Earth's surface, but from far above it. Picture the Sun at the center with the planets spread out around it in a broad flattened disk. This disk has two sides. One can be called north, the other south, but those names are conventions, not cosmic truths. Astronomers define the north side of the solar system based on the direction of Earth's orbit and the tilt of Earth's axis. From that chosen side, most planets move around the Sun anti-clockwise, and most of them rotate anti-clockwise as well. If the entire scene were viewed from below the disk instead, everything would appear reversed. Orbits that looked anti-clockwise from above would now look clockwise. Rotations would flip too. Nothing physical would have changed. Only the description would be different. This is where confusion often creeps in. It is tempting to think of anti-clockwise as a property of the planets themselves, as if they are somehow choosing a special direction that exists independently of observation. In reality, the planets are simply spinning. The labels are human conveniences layered on top of that motion. This does not make the pattern any less real. What matters is not the word anti-clockwise, but the shared sense of rotation. The planets agree with one another. They turn in the same direction relative to the plane of the solar system. That agreement remains true no matter which side of the disk is chosen as the viewing point. The idea of reference frames helps make this clearer. A reference frame is simply a chosen point of view from which motion is described. On Earth, this happens constantly without much thought. Standing on the ground, it feels natural to say that the sun rises in the east and sets in the west. From a broader perspective, Earth is rotating, and the sun is not rising at all. Both descriptions work within their chosen frames. In space, reference frames become even more important. A spinning planet does not carry a tag that says clockwise or anti-clockwise. It simply rotates around an axis. Whether that rotation appears one way or the other depends on the observer's position relative to that axis. Move to the opposite side and the apparent direction flips instantly. This is why astronomers always specify the viewpoint, even if only implicitly. When discussing the solar system, the agreed reference frame is usually one that looks down on the plane of the planets from the north side. Within that frame, the shared rotational direction becomes obvious and consistent. Without that agreement, conversations about direction would quickly become tangled. This perspective dependence also explains why some descriptions can sound contradictory at first. For example, Earth rotates from west to east. This is often stated as a simple fact. But that description assumes a viewer standing on Earth's surface, using the familiar directions of a map. From above the North Pole, that same motion is described as anti-clockwise. From above the South Pole, it becomes clockwise. All three statements describe the same physical motion. None of them are wrong. They simply belong to different frames of reference. Planets behave the same way. Mars rotates from west to east when described in surface directions. From above the solar system's north side, it rotates anti-clockwise. From the opposite side, it rotates clockwise. The underlying motion has not changed, only the language has. This can feel unintuitive because everyday experience rarely requires switching frames so freely. On Earth, directions feel fixed. Up stays up, north stays north. But even here, those ideas are conventions tied to gravity, geography, and habit. In deep space, those anchors disappear. There is also a subtle difference between rotation and orbit that sometimes adds to the confusion. Rotation refers to a planet spinning around its own axis. Orbit refers to a planet moving around another object, such as the Sun. In the solar system, both motions share the same general directional sense when viewed from the agreed reference frame. The planets orbit the Sun anti-clockwise, and most of them rotate anti-clockwise as well. This shared alignment is the important point. It would be possible for a planet to orbit one way and rotate the opposite way. Venus does exactly that. It moves around the Sun in the same orbital direction as the other planets, but its rotation is reversed. This makes Venus stand out, not because clockwise or anti-clockwise is special, but because it breaks the shared agreement seen elsewhere. Without a clear understanding of perspective, Venus can seem more mysterious than it needs to be. It is often described as rotating backwards, but backwards relative to what? The answer is always relative to the chosen frame. Venus simply spins in the opposite sense compared to most other planets in the same system. This is not a moral failing. It is a historical outcome. Another common misunderstanding is the idea that anti-clockwise has something to do with north, being up on a page or screen. Maps often place north at the top, but this is a design choice, not a law of nature. Space does not care about page orientation. The solar system could be drawn rotated 90 degrees, or upside down, and the physics would remain unchanged. What remains consistent is the relationship between the planets themselves. They share a plane, they share an orbital direction, and most of them share a rotational direction relative to that plane. That relationship is the real signal, not the words used to describe it. Once this is understood, discussions about planetary rotation become much calmer. The emphasis shifts away from labels and towards structure. The question stops being why anti-clockwise and becomes why shared. Why do so many planets agree on how to turn, regardless of which words are used to describe that turning? By gently setting aside the idea of absolute direction, the solar system becomes easier to understand, not harder. Motion becomes something relational rather than fixed. Patterns become clearer. Exceptions stand out more honestly. Anti-clockwise is not a rule of the universe. It is a description chosen carefully to help reveal a deeper consistency beneath the motion of worlds. And once that consistency is seen, the choice of words fades into the background, leaving only the quiet agreement that has been there all along. At first glance, the solar system appears three-dimensional and untidy. Planets circle the sun at different distances, some close and fast, others slow and remote. Their paths stretch across enormous spans of space, unfolding over years, decades, and centuries. From within it, the system feels spacious and complex, with no obvious sense of order or structure tying everything together. But when the solar system is viewed from a distance, a quieter pattern becomes clear. Almost all of the planets orbit the Sun within a remarkably thin, flattened region of space. Their paths do not scatter wildly above and below one another. Instead, they trace out gentle, nearly circular tracks that sit close to a shared plane, like grooves pressed into a vast disk. Compared to the overall size of the solar system, this plane is strikingly narrow. This flatness is not subtle once it is noticed. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all orbit within a few degrees of the same plane. There are small tilts and slight deviations, but nothing that resembles randomness. Even the asteroid belt follows this same broad arrangement, with countless rocky fragments moving within the same flattened region around the Sun. This shared orbital plane is one of the most important clues to how the solar system formed. If the planets had formed independently, or if they had been captured one by one from different regions of space, their orbits would point in many directions. Some would loop far above the Sun's equator, others far below it. Over time, the system would resemble a loose swarm rather than an orderly disk. That is not what is observed. Instead, the planets move as though they were gently laid out on a single surface, each tracing its own path while agreeing on where that surface lies. This agreement hints strongly at a shared beginning, shaped by motion long before planets existed. Flat systems do not arise by chance. They are a natural consequence of rotation. When a cloud of gas and dust begins to collapse under its own gravity, it almost never does so in complete stillness. Even a tiny amount of initial motion, barely noticeable at first, becomes increasingly important as the cloud shrinks. As material falls inward, that faint motion speeds up, and the cloud begins to rotate. As rotation strengthens, something subtle but powerful happens. Motion perpendicular to the axis of rotation becomes harder to sustain. Particles moving above or below the developing plane collide, interact, and exchange energy. Over time, these vertical motions are reduced, leaving most of the material confined to a flattened disk. This behavior is not unique to space. It appears in many rotating systems. Water swirling toward a drain spreads into a thin sheet before disappearing. Spinning dough flattens as it stretches outward. Saturn's rings exist as a disk rather than a sphere for the same reason, shaped by rotation and countless gentle interactions. The solar system followed this same logic. The shared orbital plane tells us that the planets formed within a rotating disk of gas and dust. That disk established a preferred plane early on, and once it did, it guided everything that followed. Planets grew within it. Smaller disks formed around those planets, giving rise to moons. The structure repeated itself at different scales, each shaped by the same underlying motion. This flatness connects directly to the shared direction of planetary rotation. When planets form inside a rotating disk, their orbits naturally align with the disk's motion. They move around the Sun in the same direction that the disk itself is turning. But something more subtle happens as well. The material that falls onto a growing planet carries the disk's motion with it. That material does not arrive evenly from all directions. It comes primarily from within the plane of the disk, already moving in a preferred direction. As a result, planets tend to inherit not only the plane of motion, but the direction of motion too. The flatness of the solar system and the shared spin of its planets are not separate mysteries. They are two expressions of the same formative process. Orbital alignment provides the foundation upon which rotational agreement is built. Without a shared plane, there would be no reason for planets to rotate coherently. Each world would form from material arriving at random angles, spinning however chance allowed. Instead, the disk quietly shaped every growing world. Even the small deviations fit naturally into this picture. No disk is perfectly flat. Gravitational interactions, lingering turbulence, and distant encounters can introduce slight tilts over time. Planets can gently nudge one another across billions of years. These effects add texture rather than chaos, leaving the overall structure intact. The solar system's flatness also explains why eclipses and planetary transits are possible, and why alignments occasionally grace the night sky. These events rely on the fact that the planets move within the same broad sheet of space. Without that shared plane, such moments would be rare or impossible. There is a quiet elegance in this arrangement. The solar system did not need to be flat. Space places no requirement on such order. Gravity could have assembled something far messier, but rotation gradually smoothed away excess motion, leaving behind a calm geometry that persisted. Once established, that geometry became a kind of memory. Every orbit traced today follows a path laid down during the system's earliest moments. Every shared direction of motion reflects the same ancient rotation. The planets differ wildly in size, composition, and appearance, yet they remain united by this inherited structure. In this way, flatness is not a limitation. It is a record, preserving the story of a time when the solar system was not a collection of the worlds, but a single drifting cloud, slowly turning long before planets had names at all. Long before the sun shone, before planets traced their paths or days had any meaning at all, the solar system existed in a much quieter form. There was no central star, no distinct worlds, no clear boundaries. Instead, there was a vast cloud of gas and dust drifting through space. It was cold, diffuse, and unremarkable, one of countless such clouds scattered across the galaxy. From the outside, there was nothing about it that suggested it would one day become a system of planets, let alone one with such a clear sense of order. This cloud was mostly hydrogen and helium, the simplest and most abundant elements in the universe, mixed with tiny grains of heavier material forged in earlier generations of stars. These dust grains were sparse, floating far apart, yet they played an important role. They gave the cloud texture. They allowed heat to radiate away. They helped the cloud respond to gravity more effectively. For a long time, nothing dramatic happened. The cloud drifted gently, shaped by faint gravitational pulls, distant shock waves from exploding stars, and the slow tides of the galaxy itself. Inside it, particles moved in all directions, colliding softly, exchanging energy, wandering without purpose. There was no sharp boundary between the cloud and the space around it. It simply faded into the background of the galaxy. Then gradually gravity began to matter more. Perhaps a nearby supernova sent a ripple through the cloud. Perhaps it passed through a denser region of the galaxy. Perhaps its own slow cooling allowed gravity to gain the upper hand. The exact trigger is not fully known, and it does not need to be dramatic. What matters is that once gravity began to dominate, the cloud started to change. Material began to drift inward. This inward motion was not uniform or perfectly symmetrical. No natural system ever is. Some regions were slightly denser than others. Some particles were moving a little faster. Some directions offered less resistance. As gravity pulled everything closer together, these small differences became more important. And this is where spin enters the story. The cloud did not begin with no motion at all. That would be extraordinarily unlikely. Even the emptiest regions of space contain subtle flows, tiny currents, and gentle rotations inherited from larger structures. The presolar cloud already carried a faint sense of movement, a barely noticeable overall twist. At first, that motion was insignificant. The cloud was enormous, and the rotation was spread thinly across a vast volume. But as gravity caused the cloud to contract, that same amount of motion was squeezed into a smaller and smaller region. As the cloud shrank, its rotation naturally sped up. This is not because any new force was added, or because something reached in from outside and spun it like a wheel. It happened because motion has a tendency to persist. Once something is moving, it resists stopping. When the size of a rotating system decreases, the rotation becomes more noticeable, simply because there is less space over which to spread it. This process is quiet and unavoidable. A slowly turning cloud does not need encouragement to spin faster as it collapses. It does not need guidance or fine-tuning. The increase in rotation is a direct consequence of shrinking while conserving motion. As gravity pulls matter inward, rotation emerges naturally, not as a special feature, but as an inevitable outcome. As the presolar cloud continued to contract, its rotation became clearer. What was once an almost imperceptible drift turned into a gentle, steady spin. The cloud was still enormous, still cold, still lacking a central star, but its future shape was already being decided. Rotation began to shape the collapse. Material falling inward did not move straight toward the center. Instead, it followed curved paths, influenced by the cloud's growing spin. Particles approaching from different directions interacted, collided, and gradually settled into patterns that favored motion around the center rather than directly into it. Over time, this led to a subtle but important change. The collapsing cloud began to flatten. Material moving in the direction of the rotation found it easier to remain in orbit around the growing center. Material moving strongly above or below the developing plane collided more often, losing energy and settling closer to that plane. Slowly, almost imperceptibly, the cloud transformed from a loose three-dimensional shape into something flatter and more organized. All of this happened without intention. There was no moment when the cloud decided to become a disk, no boundary where chaos suddenly gave way to order. This structure emerged gradually, guided by gravity and motion working together over immense spans of time. At the center of this spinning, flattening cloud, density increased. More and more material gathered into a growing core. Temperatures rose as particles collided more frequently. Pressure built. Eventually, conditions became right for the birth of a star. But even before the sun truly ignited, the system already had a direction. The rotation of the cloud defined a sense of orientation that everything else would inherit. The disk that formed around the central region carried that rotation forward. The material within it moved together, sharing the same general sense of spin. This was not imposed later. It was present from the very beginning. What is striking about this process is how little it depends on special circumstances. The cloud did not need to be perfectly shaped. It did not need to rotate quickly at first. It did not need to experience a violent trigger. Any small initial motion, combined with gravity and time, would have led to the same general outcome. Rotation in this context is not an extra feature added to the system. It is a natural consequence of collapse. This is why spinning disks are so common in space. Stars form with disks around them. Planets form within those disks. Galaxies themselves often take on flattened, rotating shapes. The same basic physics applies across an enormous range of sizes. The presolar cloud was simply following a pattern written into the behavior of matter and motion. As collapse continued, the disk became more pronounced. Material within it moved in orderly paths circling the growing sun to be. The sense of direction became clearer. The flatness became more defined. The stage was set for planets to form. By the time individual worlds began to emerge, the system's overall rotation was already well established. The planets did not choose a direction. They inherited one. Their shared spin is a direct echo of that earliest motion, preserved through billions of years of change. In this way, the story of planetary rotation begins not with planets at all, but with a drifting cloud slowly gathering itself, quietly turning as it did so. There was no forceful push, no deliberate spin, only gravity, motion and time working together in the simplest way possible. And once that motion existed, it never truly went away. Spin has a remarkable persistence. Once motion begins, it does not like to disappear. It can change shape, shift speed, or spread itself out, but it resists being erased entirely. This quiet stubbornness is one of the most reliable behaviors in nature, and it plays a central role in explaining why planets continue to rotate in the way they do. The idea behind this persistence is often called angular momentum, but the name itself is less important than the behavior it describes. At its heart, it is simply the tendency of rotating motion to be conserved. When something is spinning, that spinning wants to continue unless something actively interferes with it. This is not an abstract rule invented by physicists. It is something experienced in everyday life, even if it is rarely noticed. A slowly turning playground carousel will keep rotating for a long time if nothing touches it. A figure skater spinning on ice will continue to turn smoothly until friction with the air or the ice gradually slows them down. In space, where friction is minimal and distances are vast, this tendency becomes even more pronounced. The pre-solar cloud that gave rise to the solar system already carried a small amount of rotation. That motion did not vanish as the cloud collapsed. Instead, it was preserved, carried inward, and reshaped as the system evolved. Gravity pulled material closer together, but it did not cancel the motion that was already present. This is the key idea. Motion is not easily destroyed. It must be transferred, spread out, or redirected, but it does not simply fade away on its own. In a collapsing cloud of gas and dust, there is nothing efficiently draining away rotational motion. As a result, whatever spin exists early on becomes an enduring feature. As the cloud shrinks, something counterintuitive happens. The rotation speeds up. This is not because gravity actively twists the cloud faster, or because an external force reaches in and accelerates it. Instead, the increase in speed comes from the same motion being confined to a smaller space. An everyday analogy helps make this clear. When a skater pulls their arms closer to their body while spinning, they rotate faster. Nothing magical has happened. No new spin was added. The same rotational motion is now concentrated nearer to the center, making the turning more rapid. The collapsing cloud behaves in much the same way. Early on, the cloud was enormous. Its rotation was spread thinly across a vast volume. As gravity caused the cloud to contract, that same rotation became more noticeable. The system had less room to distribute its motion, so the spinning grew stronger. This relationship between size and spin is deeply reliable. Shrinking systems spin faster because the motion they already possess has nowhere else to go. Importantly, this does not require precision or balance. The cloud does not need to collapse evenly. It does not need to be perfectly round. It only needs to shrink while retaining its motion, and gravity ensures that both conditions are met. As the pre-solar cloud continued to contract, angular momentum shaped its behavior at every stage. Material falling inward followed curved paths rather than straight lines. Collisions between particles redistributed energy, but the overall rotation remained. The developing disk around the young sun carried the same sense of spin as the original cloud. Even when matter clumped together to form planets, this persistence continued. As planets grew, they accumulated material that was already moving within the disk. Each grain of dust and each fragment of rock carried a tiny contribution of rotational motion. When added together over millions of years, these contributions built up into a clear, measurable spin. This is why planetary rotation feels inherited rather than imposed. The planets did not need to be spun up later. They did not require a special event to set them turning. Their rotation emerged naturally as a result of growth within a spinning environment. The motion was already there, waiting to be gathered. Once a planet had acquired a certain amount of spin, that motion became remarkably difficult to erase. To significantly alter a planet's rotation requires either sustained interaction over immense periods of time or a dramatic, well-aimed collision. Small impacts tend to average out, nudging the planet slightly, but rarely overturning its overall direction. Tidal forces can slow rotation, but even these act gradually, taking billions of years to make major changes. This is why the direction of spin is so stable across the solar system. Speed can change, axes can tilt, days can lengthen or shorten, but the fundamental sense of rotation tends to persist because it is rooted in the system's earliest motion and protected by the conservation of spin. Even exceptions follow the same logic. Venus, for example, rotates in the opposite direction to most planets. This is not because it ignored the rules of angular momentum, but because its history likely included extreme interactions that altered how that conserved motion was expressed. The underlying principle still applies. The spin was not forgotten, it was transformed. Uranus, with its dramatic tilt, offers another example. Its unusual orientation suggests a violent past, perhaps involving massive impacts. Yet beneath that tilt, its rotation still carries the imprint of the original disk. The motion survived, even as the planet's posture changed. What emerges from all of this is a picture of remarkable continuity. From a drifting cloud to a spinning disk, from a growing star to orbiting planets, the same rotational story is carried forward. Angular momentum acts like a memory embedded in motion itself, preserving information about the past long after the original structure has changed. This memory does not fade easily. It is passed along quietly, reshaped, but not erased. In the vacuum of space, where friction is scarce and time is abundant, this persistence becomes one of the dominant organizing principles. Systems evolve, but they do so while respecting the motion they already have. Spin is not added casually, and it is not removed lightly. This is why the solar system feels coherent. The planets rotate in a shared direction because they inherited a shared motion. That motion was strengthened as the system shrank, gathered as worlds grew, and preserved as those worlds matured. It was never forgotten, because nothing ever truly asked it to leave. In this way, spin is not a detail layered onto planetary formation. It is a foundational feature, woven into the process from the very beginning. Once motion begins, it tends to remember itself, and in the vast calm of space, that memory can last for billions of years. As the collapsing cloud continued to shrink, its future became clearer. The growing rotation did not remain evenly spread throughout the cloud. Gravity pulled material inward, but rotation resisted a straight fall toward the center. The result was a compromise. Matter moved closer, but it did so while circling, gradually arranging itself into a broad spinning disk surrounding a denser core. At the heart of that disk, the sun began to form. Material near the center grew increasingly compressed. Collisions became more frequent. Temperatures rose steadily as particles packed closer together. Eventually, the central region became dense and hot enough to mark the birth of a young star. But even as the sun ignited, it did not consume all the surrounding material. Much of the cloud remained spread out in a rotating disk that encircled the newborn star. This disk was not a thin, delicate structure at first. It was thick, turbulent, and full of motion. Gas and dust swirled in overlapping paths, colliding, sticking, and separating again. Yet beneath this apparent complexity, the disk shared a simple and important feature. Everything within it was moving in roughly the same direction. The sun formed inside this rotating environment, not separate from it. This arrangement explains something fundamental about planetary systems. Stars do not usually form alone, they form with disks. Wherever gravity gathers rotating material into a central object, a disk is a natural companion. The same balance between inward pull and sideways motion appears again and again throughout the universe. Disks are common because they are efficient. When matter collapses while rotating, it cannot fall straight inward without shedding motion. Instead of stopping, that motion redirects material into orbit. Over time, repeated interactions flatten the system, guiding matter into a disk where rotation and gravity coexist peacefully. This configuration allows material to remain close to the star without immediately plunging into it. That balance is remarkably stable. In a disk, particles can collide gently, exchange energy, and slowly evolve without disrupting the overall structure. Motion becomes organized rather than chaotic. Paths become predictable. Over long periods, this stability allows complex processes to unfold, including the growth of planets. This is why disks appear so often in space. Young stars are frequently observed with glowing disks of gas and dust around them. These disks can stretch for billions of kilometers, shining faintly as they reflect and emit light. Telescopes have captured images of such disks in various stages of development, some smooth and continuous, others carved into rings and gaps by emerging planets. The same pattern appears on much larger scales as well. Galaxies often take the form of vast rotating disks, flattened by rotation and shaped by gravity over billions of years. Saturn's rings follow the same principle on a smaller scale. Wherever rotation and gravity interact over time, disks tend to emerge. The disk around the young Sun was no exception. Within this disk, the direction of motion became firmly established. All material shared the same general sense of rotation, inherited directly from the original cloud. There was no ambiguity about which way was forward. The disk turned as a coherent whole, carrying gas, dust, and growing clumps of matter along with it. This shared direction mattered enormously. As material orbited the Sun, it followed paths defined by the disk's rotation. Collisions between particles tended to smooth out differences rather than amplify them. Objects moving against the dominant flow were more likely to collide and lose energy, gradually aligning their motion with the disk. Over time, the system became increasingly orderly. The disk acted like a guide, quietly encouraging agreement. This process did not require forceful correction or dramatic intervention. It happened naturally, through countless small interactions. Dust grains brushed past one another, gas swirled and mixed. Energy was exchanged gently but persistently. The result was a system in which shared motion became the norm rather than the exception. As the Sun continued to grow, its gravity strengthened. It cleared material from the innermost regions of the disk, drawing gas inward and shaping the surrounding environment. Yet the disk persisted, extending far beyond the young star, providing the raw material for planets yet to come. Importantly, the Sun's own rotation aligned with the disk. The same motion that shaped the disk also influenced the star forming at its center. As material fell inward, it transferred angular momentum to the growing Sun, causing it to spin. The star and the disk rotated together, reinforcing the system's shared sense of direction. This alignment is not perfect in every system, but it is common. It reflects the deep connection between stars and the disks that give rise to planets. They are not separate creations. They are different expressions of the same collapsing, rotating cloud. Within the disk, regions of higher density began to appear. Dust grains collided and stuck together, forming larger clumps. These clumps swept up more material as they orbited, gradually growing into solid bodies. Throughout this process, the disk's rotation continued to shape how material arrived. Incoming matter tended to add spin in the same direction rather than cancel it out. This is how shared rotation becomes locked in. Once the disk's direction was established, it became difficult for anything within it to ignore that motion. Growing objects naturally aligned their orbits and spins with the surrounding flow. The disk did not force agreement. It simply made agreement the easiest outcome. Over time, the disk thinned and cooled. Gas gradually dissipated, either falling into the sun or being blown away by stellar winds. What remained were the solid building blocks of planets, still moving within the same flattened structure and still sharing the same sense of direction. By the time planets fully formed, the system's rotational character was already deeply set. The sun shone at the center, spinning calmly. The planets traced their orbits within the disk's plane. Their rotations reflected the motion of the material from which they grew. What began as a faint twist in a drifting cloud had become an organizing principle for an entire planetary system. This sequence is neither rare nor fragile. Across the galaxy, young stars repeat the same pattern. Disks form, stars ignite, planets emerge, shared motion persists. The details differ from system to system, but the underlying process remains strikingly consistent. The birth of the spinning disk is the moment when direction stops being ambiguous and starts becoming history. From that point on, the system remembers how it turned. Everything that followed, from the spin of planets to the arrangement of moons, carried the imprint of that early rotation, not because it was imposed later, but because it was present from the very beginning. The disk did not merely surround the sun, it defined the future. Planets are not born all at once, they grow. Inside the spinning disk surrounding the young sun, matter did not suddenly assemble into fully formed worlds. Instead, growth unfolded slowly, through countless small steps, guided by gravity, motion, and time. This process is known as accretion, and it is far less dramatic than the word might suggest. At first, accretion involved dust grains no larger than grains of sand. These tiny particles drifted through the disk, moving along similar paths, carried by the shared rotation of the surrounding gas. When they met, they often stuck together, not because of forceful collisions, but because gentle contact allowed electrical forces and surface textures to bind them. Over time, these small clumps became larger ones. Pebbles turned into rocks, rocks merged into boulders, boulders gathered into objects kilometers across. Each step was slow and uneven, with long periods of calm punctuated by occasional collisions. Nothing about this process required speed or violence. In fact, gentle interactions were far more effective than destructive ones. As these growing bodies moved through the disk, they swept up material that was already in motion. This is the key to how planets inherit spin. Every piece of material in the disk was orbiting the sun in the same general direction. Each grain of dust carried not only mass, but also motion. When that grain became part of a larger object, its motion did not disappear. It added to the motion of the growing body. One grain made almost no difference. Millions did. As accretion continued, the combined effect of all this incoming material built up into a clear sense of rotation. The growing planet did not need to be spun like a top. It accumulated spin naturally, simply by collecting matter that was already moving. This process favors consistency. Material approaching a growing planet from the disk tends to arrive along paths shaped by the disk's rotation. Collisions that add spin in the dominant direction are more common than those that cancel it out. Over time, contributions in the same direction reinforce one another, while opposing motions tend to average away. The result is a planet that rotates in harmony with its surroundings. It's important to distinguish here between two related but separate motions. Orbit describes a planet's movement around the sun. Rotation describes a planet spinning around its own axis. Both motions emerge from the same rotating disk, but they are not the same thing. A planet can orbit without rotating, at least in principle. It can also rotate without orbiting another object. In the solar system, however, both motions share a common origin and often a common direction. The disk set the rules for orbit first. As material circled the young sun, it naturally settled into stable paths around it. Growing planets followed those paths, becoming locked into orbits defined by the disk's plane and direction. Orbit is therefore a large-scale motion involving the entire planet traveling through space. Rotation is more intimate. Rotation concerns how the planet turns around its own center. This motion develops as the planet gathers material from different directions, each contribution adding a small twist. Over time, these twists combine into a steady spin. Although orbit and rotation are distinct, they are closely linked by history. Because the same disk shapes both, they often align. Most planets orbit the Sun in one direction and rotate in that same general sense. This alignment is not guaranteed by any single rule, but it is strongly encouraged by the way accretion unfolds. As planets grow larger, their gravity becomes stronger. They begin to dominate their local regions of the disk, pulling in material from a wider area. This material still carries the disk's motion, and its arrival continues to reinforce the planet's spin. Once a planet reaches a certain size, its rotation becomes increasingly stable. Small impacts can nudge it slightly. They can speed it up, slow it down, or tilt its axis, but reversing its spin entirely becomes difficult. The accumulated motion from millions of smaller contributions has momentum of its own. Changing direction now requires something dramatic. This explains why the basic direction of rotation tends to survive the planet's formation. It also helps explain why rotation rates vary so widely. Different planets grew in different environments. Some formed quickly, sweeping up material efficiently. Others grew more slowly, interacting with gas for longer periods. Some experienced major impacts that altered their spin, while others avoided such disruptions. These differences affect how fast a planet rotates, but they do not usually erase the inherited direction. Rotation speed is flexible. Rotation direction is resilient. The surrounding gas also played a role during these early stages. Gas flowing past a growing planet could apply gentle torques, subtly adjusting its spin. Over long periods, these interactions smoothed rotation rather than randomizing it. The gas acted like a soft, persistent influence, encouraging alignment rather than disorder. As the disk evolved, gas gradually thinned and dispersed. Once it was gone, the planets were left largely on their own, carrying the spins they had acquired. From that point onward, only major events could significantly alter their rotation. This is why the imprint of early motion remains visible billions of years later. Planets today are not actively inheriting spin from a disk. They are preserving the result of a process that ended long ago. Their rotations are fossils of formation, records written in motion rather than stone. The difference between orbit and rotation becomes clearer when considering exceptions. Venus orbits the Sun in the same direction as Earth and Mars, but it rotates in the opposite sense. This tells a specific story. Venus likely formed within the same rotating disk, acquiring an initial spin aligned with the rest of the system. Later events, perhaps involving intense tidal interactions or massive impacts, altered how that inherited motion was expressed. The orbit remained stable, the rotation changed. Uranus provides another example. Its orbit fits comfortably within the solar system's shared plane, but its rotation axis is dramatically tilted. The planet still spins, still carries the imprint of formation, but its orientation was reshaped by later events. These cases underline an important point. Orbit reflects the large-scale structure of the system. Rotation reflects the detailed history of growth and interaction. Both are rooted in the same origin, but they respond differently to change. For most planets, the early conditions were gentle enough that inheritance remained clear. Accretion built worlds slowly, spin accumulated steadily, direction was preserved. In this way, planetary rotation is not a choice made by the planet. It is not a preference or a rule imposed from outside. It is a natural outcome of growing within a shared rotating environment. Each planet carries that environment within it, long after the disk itself has vanished. The slow gathering of dust and rock did more than build mass. It gathered motion, piece by piece, until entire worlds were quietly set turning.